Thank you. So my name's Mark, and I've been working on this library for a while now. It's an array programming library, and so basically this is the first time I'm kind of presenting it to the Python world. So what is DyND? It's a component of the Blaze project, which is a fairly large-scale project we're developing at Continuum. It's a dynamic programming library, so that means there's an array data structure. It's got an array-oriented type system. It does deferred computations, and it's very much a work in progress. So what I'm going to show you is maybe some of the slightly more polished subsets of what I've developed so far, but it is definitely something that is being actively developed, and there are big gaps in what I've implemented and what's still missing. So a big question to ask is, why not NumPy? Why not just either isn't NumPy good enough, or can't we just do all this development within NumPy and evolve that system? Well, so we want to extend the array programming model that NumPy allows. So adding more types, doing things like ragged arrays, so data that's not just fixed dimension sizes, having more things like act like views. Like, say, if you do fancy indexing, well, wouldn't it be nice to be able to assign to that and have that kind of scatter back into the original data? But people depend on NumPy being stable. Like, there's code that they've written that they've been using for years. If we were to just change NumPy too much, a lot of code will break. That's not a good thing. And what that means is that if we're actively developing within NumPy, we have to develop more slowly and be careful, like have careful beta, alpha periods of every release to give people sufficient time to test their stuff and bring it in. If we want to do a significant change, it requires a lot of discussion to be able to come to a consensus that it's like, this is something that we want to put into the library that's at the core of the scientific Python stack. So by starting a fresh library, we can revisit a lot of the design choices that were made in NumPy, and we have a place where we can experiment. We can try a lot of things and like change our minds when we find out that it's like, oh, those weren't the right choices, and do that many times until we iteratively kind of arrive on a new model, a new data structure that's maybe going to be a little bit, hopefully, better than NumPy, but still satisfy the same cases that people are using NumPy for. So I'm going to switch to some notebooks that I've got and basically go through and demonstrate what DyND looks like. So this is the standard import looks like this, basically. In NumPy, some people do import star, other people do import NumPy as NP. I'm a big fan of using a separate namespace for it, and so I've kind of baked into the library the notion of doing it that way. So what that lets me do is put some things that would conflict with NumPy's global namespace in there, so there might be some more natural spellings of things because of that. So basic usage looks very much like NumPy. You create a DyND array out of some NumPy data. It looks very similar to NumPy. One difference you'll notice here is that there's this strided dimension thing. That's the dimensionality goes into the type. In NumPy, the D type doesn't represent any dimensionality, so that the array object is where all that goes. We've chosen to build this library so that that dimensionality is going into the type. So if we do like a two-dimensional example like this, you can see now there's two strided dimensions ahead of the D type of this array. One thing that's still missing is the pretty printing is not very good. So some of the things that I'll print will look a little bit messier. So one thing that's been a bit of a problem in NumPy is dealing with arbitrary string data. So there's basically two approaches most people take. One is the built-in strings that NumPy has, but they're fixed size. So if you have like, say, a bunch of small strings and one giant string, it's like you'll be wasting memory, or like you can kind of run into issues. If you pick a size and later you need to assign a bigger string, that might be annoying. So DyND has a separate string type, which is a variable size string. It's not, so you see here NumPy has looked at all of the strings, and it saw that the maximum size is 4, so it's given an array of maximum string size 4. In DyND, I've got an array of strings that are they're just strings. So doing ragged arrays where you have something that looks like this, the outer dimension is 3, but the next dimension is different sizes. So this will behave a little bit different. It's not going to interact 100% smoothly with array programming, but there's a lot of ways you can mix this with NumPy's array programming style, and it would be nice to have things work together with this. So the data structure works by adding a variable dimension. So this kind of ragged array gets represented as a strided dimension on the outer side, a variable dimension in the middle, and then this is int32. So NumPy does do something if you give this data, but it's even maybe a little bit ambiguous to see what is this object. If I think I know what it is, and it's a one-dimensional object array, and the objects are these lists. There's still Python lists that are sitting there. So since DyND is part of Blaze, it speaks the type system we've developed for Blaze called datashape. And it provides a nice way to spell record types or structured arrays. So here's a little example of a few of the talks during this conference kind of put into a table. So this UD type stands for the uniform D type. So we're not specifying the arrayness of this input that's deduced by the system. But we'll give a title, which is a string, a presenter, a time. So there's a very primitive still date time built in. So we'll say based on minutes and a room number. And so the data for that is very much like how it is in NumPy. The one problem with that at the moment is that, once again, the formatting hasn't been worked on very much, so this does look very messy. But so to show you a little bit what you can do with this kind of record array, accessing fields is just by Python attributes, kind of like NumPy has a rec array object in it, but it's a separate thing. It's not kind of how you do things by default. You have to request it specially. In DyND, that's just how it works. We get the room number just like that. Or in the same way, or to get the same data, we can use indexing. So the record dimension, or you can think of the record type as another dimension. It's kind of a heterogeneous dimension in some way. So if we ask for the index 3 along that dimension, it's exactly the same thing. And what's neat about that is we can now slice it. So if we slice in the record, there's just the title and the presenter of our talks, for example. So another operation that I've done a little bit of work to do is a very simple group by operation. What it does is it takes the array of data and then an array of by, like what are we grouping by. So in this case, we're going to group our data by the room number. So when we do that, well, there were 3 room numbers in our tiny data set. And so because the printing is messy, I'm not going to print the whole thing because it would be hard to see exactly what the type it produces is. But it's a ragged array where the first dimension will have size 3 and the second dimension is going to be variable. And so if we want to see like what are all the talks that were in room 203, that's these two, the spider one and this talk in my little list. So to kind of show another example using the date time that's in there. So the date time, if we want to group by the date, we have to get the date out of that date time. So in DyND, that's represented by a date property on the date time. So we can just grab that date, group by it, and there's our 2 dates that talks are given within that data set. And so if we want to look at what are the talks that are given today, there we have a matplotlib and this talk again. So one final kind of little bit of this, the Python side of things here is I'll show you a way you can kind of create some views that are not sort of ordinary views like in NumPy. They're backed by an expression. I mean, you can think of it like how you do properties in Python with a getter and a setter. It's very similar to that. So we'll start with an array of strings. This time, I'm going to make a NumPy compatible string type here. So it's a size 10 ASCII string. And we can grab the string. It's very simple. So let's do a uniform cast to the date type. That means like below all of the array dimensions, we cast it to a date. And now if we look at that, so now it's not just a date that we've got. It's actually something which is a view on top of the string that we started from, and it's a conversion to date. So it's a deferred operation type. And we can see the value at 0 is the same date that we had as a string. And so the date, it's not very fleshed out, but one example operation is kind of like the date object built into Python has a replace function where you can substitute different month, year, day. So we'll just do a replace of the month to 3. And you'll notice we're doing that on the date array. That's kind of like this view of the string array. But now if we look back at the string array at 0, we can see that it's been modified. So where before it was July, now it's March. So we were doing a date operation on kind of this view of strings. So it's kind of a more generalized way of thinking of NumPy views. And so to finish off this part, the way it can connect to NumPy is it speaks the buffer protocol, so where possible, it'll just naturally work in NumPy. But I've got a function here which does a bit better error checking. And anyways, we can use that to convert to a NumPy array. And you'll see that it's actually a view into the original string data here. So if we modify the NumPy array, now look back at the date view array that we had, that's also been, it's reflecting the changes. It's actually viewing that string data we had. So for a little bit, so that to kind of give a taste of like how does this work under the hood, I'm going to go just a little bit over some of the details of how does this work. So I'll go a little bit quickly, but for those of you who have developed on NumPy, hopefully it gives a bit of a taste as to how you might generalize NumPy to support ragged arrays. So I'll go a little bit quickly. So we start with a NumPy array here, a 2-dimensional array. And you should hopefully know that it's made the way it's laid out is described by a shape and a strides attribute of the array. And so this is a little way we can look at the address, and using C types to directly access the memory of the array, we can see that that's kind of equivalent to using NumPy. And you can kind of do this dot product between your index and the shape, and you get an offset. And you can kind of see that's equivalent. So if you look at this memory address here, 844, let's now convert that to a DyND array. And there's a low-level namespace which gives access to some of the direct memory representation that's happening in DyND. So it kind of lets you get to the guts of it with this. But so that same 844 memory address is here where we're accessing B12. It's looking at the same data. As a way to sort of explore this, I've created a debug repr method, which will basically print out like what is DyND doing under the hood here. And so the strided dimensions each get corresponding array-level metadata that describes what the dimension or how the data for that dimension gets laid out. So instead of having strides in one array and sizes or the shape in another array, each strided dim gets its own little piece of this metadata. And so if I skip a little bit and go down to the next example, a ragged array. So that's a strided dim of var dim. And so the strided dim gets the first piece of the array metadata in the same fashion, but now the var dim gets the second piece, and it's a slightly different. So if we look at the debug repr of that, the first strided dim gets this stride and size, just as before, but now the var dim gets a stride and an offset and a reference into another memory block where the actual data goes. So just to kind of final one here, the string works in a similar fashion. So if we look at its debug repr, the string gets a similar metadata where it holds on to a reference to the data for it. So I think I'll finish up. So DyND, it's very much a work in progress. I've showed you some of the kinds of things it did. Hopefully demonstrated effectively that there's some things that by creating a new data structure, we can kind of get a slightly better array programming model. So you can go to wakari.io or use Anaconda. DyND is included in that as an experimental package there. It's open source. Everything I've showed you, you can clone these repositories. The notebooks I've showed you are in the DyND Python repository. And there's my contact. So, yeah.
So, yeah, you're right on time. We have 5 minutes for questions.
Yeah. Sure. Yeah. And
just out of curiosity,
yeah.
How many template arguments or member variables are there on the dtype object?
Okay, how many template?
I don't know how you implemented it, but like,
yeah.
what is it? How many things does it take to actually specify a dtype on the C++ level? How many fields are there?
Okay. Well, the way you use it is usually pretty simple. Like you there's a function which will create one, say, from a built-in C++ type. Like you say make D type with a template parameter of int, and it'll build a D type for you. I mean, there's like the size, the alignment, some flags, and a bunch. There's a structure of default parameters, which I don't remember how big it is, but maybe it's like 5 or 6. And then each dimension type can have as much additional information as it wants.
It's dynamic, right?
Yeah. Yeah, it's dynamic. Yeah.
So, from what I've seen, I really like the design of Dyn. I have a question about the broader ecosystem. So we all do very different things in this room, but the one thing that we all share is NumPy.
Yeah.
And so, what is your plan for Dyn and integration into the broader community? I can imagine, are you planning to implement students as the interface with the community, or is there a possibility of a fork happening?
Mhm.
What's your outside of design, but sort of the broader
Yeah.
design community? How does that work?
Yeah. So the question is how does DyND relate to the broader community? What are our plans for how it should integrate with other tools, or does it replace something? Or I guess I mean the simple answer is I don't know. I mean I started this without having a clear picture of what it would mean. One possibility is that for the foreseeable future, NumPy provides a stable base on which people that need their code to stay the same and work for a long time continue to use NumPy, and DyND kind of evolves at a slightly faster pace. I mean, at the point where DyND can match all the features of NumPy, then it becomes like I think that's a very big question of like how would that work? Does whether we implement like the NumPy API both at the Python level or the C level on top of DyND as a support library, or whether we do development within NumPy to kind of evolve it towards and provide like tools, kind of like the Python 2 to Python 3 evolution, or I mean, I don't know. It's hard to predict. It's like I think we're very open to suggestions and people trying it out and seeing what we might do. I mean, for now, I'd like to have both systems be side by side and use DyND as a place to play, like as a playground for possibly like date time within NumPy is something that there's active discussions recently of what it could look like. And so, I mean, I've got a simple date time in DyND. I mean, I think it would be easier to change and iterate through several versions of date time in DyND to just see what it works. And maybe once something looks good, we could port that into NumPy, for example, to like I could see some kind of dynamic like that. But, yeah. Oh, all right. Yeah.
So my question is a little bit related. It seems like the penalty for all this flexibility is that programs that are using or that are trying to anticipate these arrays can assume a lot less about what the shapes of these arrays are. So I was wondering if you thought at all about how kind of like general purpose DyND utility libraries would handle such flexible arrays.
Yeah. That's something I was thinking very seriously about when I was like trying to come up with the basic idea. It's like how can in the simple cases keep it simple and then have it scale naturally to more complex data formats and stuff. And so what I showed you of the size stride layout, I mean, one idea is to have an easy way to check that like it's a simple data type with a strided layout, in which case you just know that the binary layout of it is size stride, and maybe you can work with that directly. And if it's not in that format, then maybe some simple APIs let you conform it if necessary by making a copy or something like that. I mean, those are the kinds of things I've thought for that.
I had a more detailed question. What is the rationale to put the stride and dimension in the
Yeah, okay. The question is why to put the strides and dimensions in the D type. Well, what's in the D type here is just the fact that it's a strided dimension. So the strides and the size of the dimension are still inside the array, just like in NumPy, except they're laid out slightly differently. There is also, so in NumPy, there's the default dimensions that you get act like these strided dimensions. And there's also, within structures, you can have dimensions that are fixed shape, and they are only C order. So there's another dimension in DyND that does a fixed layout where the size and the stride are part of the type itself. And those can behave kind of like the ones in NumPy inside of structs, but a little more flexibly, like if you have a Fortran order array within a struct, DyND will support that, for example.
We just have time for one more question and then take a break.
And I can see some kind of related questions. I'm wondering, are ragged arrays fixed each row, as it were, fixed once created, and in fact, this relates to the whole thing, just one contiguous block of data?
Okay, the question is, are the arrays in a ragged array fixed size once they're created? And is it a single contiguous chunk of memory? The answer to that in this vardim is yes. It's kind of, I've tuned it towards kind of a streaming array computation model where it's like if you compute over the whole array, you're creating these variable-sized objects, but you're creating them once in a streaming computation. I do have intent to create additional, more dynamic types, and you could use one or the other depending on the style of computation and whether a streaming model that maybe will be more efficient with this type is the right choice, or a fully dynamic one, which will be less efficient if you don't need that. And whether it's in one contiguous chunk of memory or not depends on how big it is. So if it hits the end of the memory block or the bit of memory that it allocated, it can't move the beginning part, so it starts a new one. So it's kind of a bunch of contiguous blocks depending on how much data you had.
I don't know. There's a lot of interesting questions probably related to this. Do you want to take one more question?
Yeah. Sure.
One word answer. Are you planning to support sparse arrays?
Not directly within it. It's a dense array system. Or,
I don't know. It's the break now. We can
Yeah,
maybe
all
just
right.
keep
Yeah,
on.
one last question.
Yeah.
All right, one last question.
So the support for, it seems that part of the goal is to have better support for categorical quantities, which isn't found in NumPy. So I don't know how much work you've done on just performance considerations and categorizing more complex data shapes.
Yeah.
And like, just because I found in kind of business analytics like that, categorization and part of the group by is kind of where all performance is lost.
Yeah.
Sort of hashing and sort of, computing unique values or categorizing, and sort of how that, if you've done much exploration there, kind of the performance trade-offs of how you're laying out the data, just like you're, kind of having to hash these like variadic
Yeah.
data types.
Yeah, well, I've,
Try and repeat that question.
what's that? Oh, yeah. So, question about categorical data types and especially more complex data shapes and how the performance of them are, like when you get to hashing them and doing group by operations. Mostly I've focused on trying to find a way to express the group by and some of the categorical types within the system that fits right with other things. I did take a look at like Panda's vbench and try to like do some of the same operations to get some comparisons, and mostly that led me to realize some shortcomings and implement some more like support for example, doing a group by on multiple fields is supported, and it's not. Yeah, the implementation currently is. I mean, I haven't actually benchmarked it to see how good it is, but I think I've tried to do it in a fairly efficient way. I mean, it's currently based on sorting and kind of binary search sort of lookups, but I think hashing is probably better, and I need to switch to that at some point. So.
Okay, let's thank Mark for